Section 3 is about the atom, and our learning goal is to describe the electrical charge of a proton, a neutron, and an electron, and identify their location within an atom. All elements listed on the periodic table are made up of atoms. An atom is the smallest particle of an element. We're going to look at Dalton's atomic theory first. So the Greek philosophers in 500 BCE reasoned that everything must contain minute particles called atomos. The idea of atoms did not become a scientific theory until 1808. John Dalton developed an atomic theory that proposed that atoms were responsible for the combinations of elements that were found in compounds. So Dalton said, all matter is made up of tiny particles called atoms. All atoms of a given element are identical to one another and different from atoms of other elements. He also said that atoms of two or more different elements combine to form compounds. A particular compound is always made up of the same kinds of atoms and the same number of each kind of atom. For example, carbon dioxide is always going to have one carbon and two oxygen atoms. Water will always have two hydrogens and one oxygen. And fourth, a chemical reaction involves the rearrangement, separation, or combination of atoms. Atoms are neither created nor destroyed in a chemical reaction. Atoms are the building blocks of everything around us, and atoms are too small to see with the naked eye. Look at this. This is images of gold atoms that are produced when magnified 16 million times by a scanning microscope. Let's look at the electrical charges in an atom. By the end of the 1880s, experiments with electricity showed that atoms were composed of tiny particles called subatomic particles, made up of protons, neutrons, and electrons. Two of these subatomic particles were discovered because they have electrical charges. Charges can be positive or negative. Positive charges repel each other. Two negative charges repel each other. And opposite charges attract each other. Just like Paula Abdul's song that says, 'cause opposites attract. So here's showing us that positive charges repel, negative charges repel, but a positive and a negative attract each other. J.J. Thomson is another scientist that discovered that cathode rays were streams of small negatively charged particles called electrons. Negatively charged cathode rays, or negatively charged electrons, are attracted to the positive electrode, right? Because opposites attract. According to J.J. Thomson's plum pudding model, that's his model of what the atom looked like, protons and electrons were scattered throughout the positively charged cloud. So we've got negative charged electrons in this positively charged cloud. Further down the line, in 1911, a guy named Ernest Rutherford worked with J.J. Thomson and developed a new structure for the atom based on Rutherford's gold foil experiment. So here's what Rutherford did. Rutherford had a piece of gold foil, and he had this source of particles, and he shot this beam of particles through the gold foil. So the positive particles were aimed at a piece of gold foil. He thought all these particles are just going to go straight through. But here's what happened, and this kind of shows a little bit better. We have gold atoms, and while yes, a lot of particles went straight through, there were some that were deflected, some that hit and came over here. Another one hit and bounced off this way. Another one hit and bounced off this way. So there was a lot of deflected. We can see here these are undeflected. They went straight through. So here's what he came up with. We are throwing positive charges, and sometimes there was deflections. That means the positive hit something that it was repelling. So it hit something that was positive. From his gold foil experiments, Rutherford determined that atoms contained a very small region in the center that had a positive charge, and we call that the nucleus. So what was different about his claim on the atom compared to J.J. Thomson, J.J. Thomson said this whole atom was a positively charged cloud. But through this gold foil experiment, he said, no, the whole thing is not positively charged, because if I sent a beam of positive, then the whole mass would repel it. But that wasn't the case. He said this small region in the center had a positive charge, which we would call the nucleus. He also said that there's a region of space around the center that was occupied by electrons. The positively charged particles are called protons, and the negatively charged particles are called electrons. So protons are positive, electrons are negative. If an atom was the size of a football stadium, so I need you to have a vision of a football stadium, the nucleus would be the size of a golf ball in the center of the field. That's how small it would be. Now later, when scientists realized that the nucleus was heavier than the mass of the protons, they looked for another subatomic particle. They said, wait a minute, if the nucleus has 4 protons and it's heavier than the mass of what 4 protons should be, what else is in there? So they looked for another subatomic particle. Eventually they discovered that the nucleus also contains a particle that is neutral, so they called it a neutron. Let's talk about the mass of an atom. The mass of an atom is due to the protons and the neutrons that are in the nucleus. We don't count the mass of electrons because their mass is so much smaller. In fact, it takes about 1,836 electrons to equal the mass of 1 proton. And if we looked at the periodic table, currently there's 118 known elements. So that 118 protons would mean it would have 118 electrons, and that's our largest element. That's not even a tenth of what the mass of 1 proton would be. So we don't count the electrons when we're looking at the mass of an atom. Chemists use a unit called atomic mass unit, AMU. In biology, we call the Dalton, which is an atomic mass unit in honor of John Dalton. The AMU is defined as 1/12 of the mass of a carbon atom that has 6 protons and 6 neutrons. Well, 6 protons plus 6 neutrons, 6 plus 6 is 12. So if we did 1/12 of that, obviously that would be 1. So we say that the mass of 1 proton is 1 AMU, and 1 neutron is 1 AMU. The mass of all elements in the periodic table is compared to the mass of this carbon atom. Look at proton, we can say P or P plus for proton. It has a charge of +1. A neutron, we can say just N or N raised to the 0. Its charge is no charge. And then we have electron, E negative, and it has a charge of -1. For its mass in AMU, we say its mass is 1, in this case 1.007, but we usually just round to 1. Same with the neutron. Notice that these have the same mass. The electron mass, it's negligible. We don't count it when we're counting the mass of an atom. Obviously, we know protons and neutrons are located in the nucleus and electrons are outside of the nucleus. Take a minute to look over Section 3 review to make sure that you understand all of these pieces of information about atoms. Moving on to Section 4, atomic number and mass number. Our learning goal for this section is, given the atomic number and the mass number of an atom, state how many protons, neutrons, and electrons there are. The atomic number is different for each element, but the same for all atoms of that element. The atomic number is equal to the number of protons in an atom, and it appears above the symbol of an element. So for example, if I looked at sodium, it says right above sodium, 11. So its atomic number is 11. That also means it has 11 protons. Hydrogen has an atomic number of 1. Every hydrogen atom has 1 proton. This periodic table is a really great one to play around with. It's at ptable.com. I'll put the link right here. If I hover above hydrogen, notice over here I can see that hydrogen has 1 proton, has an atomic number of 1. Beryllium has an atomic number of 4. It has 4 protons. Chromium has an atomic number of 24. So there's 24 protons. Iron has 26 protons. Nitrogen over here has 7 protons. What's also cool about this is that it's color-coded, so I can see that nitrogen is green. It is a non-metal. I can look at just the noble gases, and I can find out information about them. It also shows me, highlights where the noble gases are on the periodic table. Same with the metalloids that we talked about. We can look at all of the metals, see all of the metals. So this is just a cool periodic table to get to know these elements and what the different things mean. Here are a few others that listed: carbon, copper, and gold. We could look at the periodic table and see that carbon has an atomic number of 6, so there's 6 protons. Copper's atomic number is 29, so there's 29 protons. Gold's atomic number is 79, so it has 79 protons. Hopefully you're getting the gist of it. Let's look at atomic models. All atoms of lithium, here's an atom of lithium, contain 3 protons. And all atoms of carbon, here's an atom of carbon, contains 6 protons. So I can look at that periodic table, and all lithium atoms have 3 protons. All carbon atoms have 6 protons. Select the correct number of protons in each atom. Why don't you look at the nitrogen, sulfur, and barium atoms to figure out how many protons there are. Hopefully you chose 7, 16, and 56. Now all atoms are neutral. Any atom of any element is electrically neutral, which means it has a net charge of 0, which also means it has an equal number of protons and electrons. Therefore, if we were to look at calcium on the periodic table, calcium's atomic number is 20. That means it has 20 protons. 20 protons, that means that there are 20 positive protons in that nucleus. Now if it's electrically neutral, that means I would need 20 negatives. Positive 20 minus 20 gives me a neutral atom. So it would need 20 electrons. It has a 0 net charge. Then we have the mass number. And the mass number represents the number of particles in the nucleus. And if you remember, what is in the nucleus is the number of protons and the number of neutrons. The mass number does not appear on the periodic table because it applies to single atoms only. If we look at protons plus neutrons, we only have whole number of protons and whole number of neutrons, so the mass number is always a whole number. And if you look back at the periodic table, you'll notice that on the periodic table, the number that's on there is a decimal point number, and we'll get more into that in just a minute. Looking at neutrons, we calculate the number of neutrons in an atom from its mass number and its atomic number. If I know the mass number and I subtract the atomic number, remember the atomic number is how many protons it has as well. So mass number is protons and neutrons. The atomic number is protons. So if I take protons and neutrons and subtract protons, I'm left with neutrons. Let's say the potassium has a mass number of 39. And potassium, if you look on the periodic table, has an atomic number of 19. So I'm going to take 39 minus 19 to get 20 neutrons. And if I have 20 neutrons and my atomic number is my number of protons, 20 plus 19 gives me a mass number of 39 because mass is protons and neutrons. Let's look at the composition of some elements. Hydrogen here. Hydrogen has an atomic number of 1, which also means it has 1 proton. These are always going to be the same. Notice here nitrogen has 7 as its atomic number and 7 protons. Oxygen's atomic number is 8, it has 8 protons. Chlorine's atomic number is 17, it has 17 protons. Notice that also if we're looking at atoms, the atoms are neutral. So the number of protons will also be equal to the number of electrons. Notice that 1 and 1, 7 and 7. 8 and 8. All right, now here we're given the mass number. If the mass number is 1, remember this is protons and neutrons, and I subtract protons, so 1 minus 1 is going to equal 0 neutrons. If we're told the mass number is 14 for nitrogen, 14 minus 7 would be 7 neutrons. If we're told the mass number is 16, 16 minus 8 is equal to 8 neutrons. Chlorine's mass number 37 minus 17 would be 20 neutrons. Do not just assume that the number of neutrons is equal to the number of protons. We have to take our mass number minus protons to get neutrons. Why don't you pause the video right here and work through this self-test. Let's see how you did. An atom of zinc has a mass number of 65. How many protons are in the nucleus? You need to look at your periodic table and find zinc. Zinc has an atomic number of 30, so it has 30 protons. To find neutrons, we would take that mass number that we were given, and we would subtract the number of protons to get 35. In this case, we're told that zinc has 37 neutrons, and we know that its atomic number is 30, so it has 30 protons, so 37 plus 30 would give me a mass number of 67. Here's another little quiz. Why don't you pause the video here and see if you can figure out these 3 answers. Let's look and see how you did. If we have 14 protons and 20 neutrons, the atomic number, remember, is equal to however many protons I have, so that would be 14. Its mass number is protons plus neutrons, so 14 plus 20 to get 34. What is the element? Well, if I know how many protons it has, I know its atomic number, I can look at the periodic table, and number 14 is silicon. Take a minute to look over this review to make sure that you understand the learning goals for this section.